All right, so let's sort of start to work more so downhill here with this idea. And the idea is that, well, the chain rule leaves certain artifacts behind that are evidence of the fact that a derivative was taken with respect to the chain rule. And one of those artifacts is that you'll have two bits of your function that are related by derivative. And so one of those is going to play the role of your u, and the other your u prime. And if you set u equal to the proper one in that expression that would have its u prime also in the expression, well then you can use a substitution to get to a simpler integral. So check it out. Like imagine we had, because I mean we ran a derivative for e to the 5x plus 2. And so the resulting function was e to the 5x plus 2 times 5. The chain rule left that artifact, 2 bits related by derivative. So we know what the antiderivative function is going to be here. It's going to be e to the 5x plus 2 plus c. But let's imagine that we hadn't done that. And let's imagine that we are just trying to find what this antiderivative is. And if we just like walked up to this derivative off of the street and we're trying to then find the antiderivative function, one thing that we might notice is there's one piece of our function and another piece of our function which are related by way of derivative. The 5x plus 2 and the 5 are related by way of derivative. And in fact, they're being multiplied within our expression. So then the question is, okay, like this feels chain rule-like. One of these is going to be our u, one is going to be the u prime. Well, of course here the u would be the 5x plus 2. Apply the differential to both sides. Once we've set the u, now what du is falls from here. Du is 5 dx. And hey, make the substitution. Substitute in, you're going to get e to the u times du. What's the integral of e to the u du? Well, e to a letter d of that letter is going to just be e to the u plus c, but we don't want to leave it just in this form because, well, the original problem was in terms of x, so we substitute back in, problem solved. Precisely what we were expecting, frankly. Now, what about this 5 tangent to the x to the 4th times secant squared dx? You look at that and you say, oh man, what is going on there? That's crazy. If you just ran across this integral, this antiderivative on the street, you might say, whoa, oh man, how in the world are we gonna like approach this? Well, we know how it plays out because we already ran the computation, but let's think about this if we just ran across this. One thing you could notice is that within the expression of this function that we're trying to find the antiderivative of, there's an artifact of the chain rule. There's an artifact left over where we have some piece of our function and some other piece of our function which are related by way of derivative. And in particular, those things are in a product, which is exactly what results with the chain rule. You have some bit of your function and some other bit of your function related by derivative in the form of a product. That's chain rule. This looks like something that might have come from the chain rule. So in particular, we've got to pick one of our things to be our u and one of our things to be our du, but knowing the relationship between tangent and secant squared, you know that the u would have to be the tangent x. But now here's the thing. As soon as you set u equal to tangent x, you know what the du is. Because if u is tangent x, du is secant squared x dx. And now let's run the substitution. Run the substitution here, we're going to get what? We're going to get 5u to the 4th times du. That's such an easy one to do, right? Now, if you want to think about this, we could say, okay, the constant multiple is going to be unaffected, so we could take that constant multiple out. And then whenever we apply our antiderivative technique here, we're going to get 5 times u to the 5th over 5 plus c. But actually, when you look at this here, the 5 in the numerator and the 5 in the denominator cancel, and you're simply going to get u to the 5th plus c, which actually makes sense here whenever you take a look at this result. What function has a derivative of 5u to the 4th? Well, that would just be u to the 5th. But now we can't leave our answer like so, but we're almost there because our original problem was in terms of x, so we got to get u back out of the expression, and in order to do that, we end up with tangent x to the 5th plus c. And guess what? That's precisely what we expected the antiderivative function to be. And yet, if we stumbled across this function along the street, and we were trying to find the function that produced this function by way of derivative, we were trying to compute an antiderivative, the minute that we notice that two of the bits of our function are related by way of derivative, well then, and the fact that those things are in a product, then that looks like an artifact of the chain rule, and the chain rule may well be the way to take the derivative. Set u equal to the tangent, and then secant squared comes out as the du term, or the derivative of that u, the u prime, thinking in terms of our chain rule language. And well, we ran the numbers, and lo and behold, it works. So in general, whenever you stumble across a derivative, and there's two bits of that function, well, excuse me, whenever you stumble across an antiderivative, and there's two bits of the function that you're looking at that are related by way of derivative, and those two bits might be in a product, well, hey, set one of them equal to u and the other equal to u prime, and maybe the derivative becomes doable.